Hello and welcome back to chemistry. We're going to continue going over some gas laws today. So just a quick overview. Last time we went over Boyle's law, which said there was an inverse relationship between pressure and volume. So the equation was P1 times V1 equals P2 times V2. We also went over Charles' law, which said there was this relationship between volume and temperature. So we had V1 over T1 equals V2 over T2. Today we are going to go over something called Gay-Lussac's law and also a combined gas law. So, Gay-Lussac was a French chemist, I believe. He said there was a relationship between pressure and temperature. So I have P1 over T1 equals P2 over T2. This looks very similar to Charles' law. Instead of having the volume up here, you have the pressure though. So let's go ahead and do a few examples. Like I said before, most of these gas laws can be easy if you just pay attention to the units and you slowly make sure you have the right equation and you don't make any mistakes. So, determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 degrees Celsius to 30 degrees Celsius. So on this one, we have 1 atmosphere at top, the pressure. At the bottom, we'll have the first temperature. So it's 20 Celsius. Remember, we need to convert this to Kelvin by adding 273. So plus 20, 293 Kelvin equals, we don't know the pressure here, P2. Determine the pressure change. So we don't know what the second pressure is, but the temperature is now 30 degrees, which is 303 Kelvin. Be sure to convert. So if we do the math, we'll get the answer. I want to point out again, you have to isolate the P on one side of the equation. So to do that, I will multiply both sides by 303 over 1. 303 over 1. So on this side, the 303 is going to cancel out. On this side, it will be 303 times 1 divided by 1 times 293. So essentially, it's 303 divided by 293. That's how you rearrange that equation. I know you're thinking, well, that's just easy. I learned that in algebra. Why are you even going over that? Well, keep in mind that some people are not as good in math or they have forgotten those things. So there's no harm in going over something easy. 303 divided by 293, and my answer should be about 1.03 atmospheres. Oops. Okay. Let's go ahead and go down to the next one. And really what you could be doing is you could pause the video and answer this question, and then we could compare answers. A container of gas is initially at 0.5 atmospheres and 25 degrees Celsius. What will the pressure be at 125 Celsius? So yet again, I always like to just write my equation out just to give me a good idea of what I need to do. The pressure here is 0.5 and it's at 25 degrees. So 273 plus 25. It's going to be 298 Kelvin equals, yet again, we don't know the pressure over here, P2, and 125 degrees plus 273 is 398. So I'm going to rearrange the equation to isolate this P2 on one side. So yet again, I'd have to multiply both sides by 398 over 1. And I will have 398 times 0.5 divided by 298. If I do that math, I will get 0.66 atmospheres. Okay, we're making some progress. Let's go down to the last example I have. A gas container is initially at 47 millimeters of mercury. Notice how we have a different unit here now. And 77 Kelvin. And now they're giving us Kelvin. We don't have to convert. So we have pressure over temperature equals pressure over temperature. Our pressure is 47 divided by 77. And what will the pressure be? So yet again, they want this pressure when it warms up to 25. Look how tricky they're being here. They're like, oh yeah, we're going to give you Kelvin here, but Celsius here, just to see if you're paying attention. See, they're always trying to be tricky. So we have 298 Kelvin over here. Make sure you convert. And then we will just do the math here. Yet again, we'll write it down here, 298 times 47 divided by 77 equals our answer. Now, if you do that math, you will get 181 millimeters of mercury. Okay? Millimeters of mercury. So, here's the interesting thing I didn't mention before. You can just check your own answers. So, you don't need me. Here's my example. Let's go back to our equation up here. I had pressure, 47, over temperature, 77. Okay? And then I had the pressure I'm looking for over 298. I found P2. This is the second pressure, 181. So you can just take 181, put it right here. Put your 181 right there. Then do this math. Do 47 divided by 77, get an answer. It's around 0.61. Do 181 divided by 298, it's 0.61. So these should equal each other if you did the problem correctly. And that's the beautiful thing about these gas laws. You can always just check your own answer. So just take your time, check your answers, and you should get 100%. Now let's move on down. This is something called the combined gas law. Basically, we take these two gas laws and we take Boyle's law, Charles' law, and also Gay-Lussac's law, and we just combine them all together. So the equation is pressure times volume. This looks like a lot like Boyle's law, right? Equals pressure times volume, but it's divided by temperature on both sides. So pressure times volume divided by temperature equals pressure times volume divided by temperature. In honesty, if you just remember this equation, even if you get a Charles law or a Boyle's law, you can solve all those problems with this equation. So this is an important equation to remember. Let's go ahead and do a few example problems of the combined gas law. If I initially have a gas at a pressure of 2 atmospheres, so yet again, let's just put our equation over here. So our initial pressure is 2, a volume of 23 liters, and a temperature of 200 Kelvin. So pressure, volume, temperature. And I raise the pressure to 14 atmospheres and increase the temperature to 300. What is the new volume? So I'm looking for the second volume. One thing I would advise in these problems, make sure your units match up. Since there's more information in these problems, it's going to be easier to make a mistake. Sometimes they will slip in different units. They'll give you atmospheres, but they want the answer in kilopascals or something like that. So just be aware of that. So we have 2 times 23 over 200. Yet again, this is a little bit more complicated in terms of the math. How do I get V2 on one side by itself? And the answer is, on this side, I will just multiply this side by 300 over 14. So if I do that, this will cancel and this will cancel. So I'll have V2 over here. But then I got to multiply this side by 300 over 14. So essentially, I'm going to get 300 times 2 times 23 over 14 times 200. Okay, I've seen people make that mistake before. Now, if I do this math, I should get 29.5 liters or something like that. Now, yet again, if I wanted to check it, I could take this answer and put it back in the equation and then see if it worked. I know this is the right answer, but just reminding you about that. Let's go down here. A gas takes up a volume of 17 liters. Write out your equation. See, chemistry can be very relaxing. 17 liters. Well, that's our volume. Has a pressure of 2.3. So 2.3. And a temperature of 299. I keep reminding you, but make sure the temperature is in Kelvin. Make sure the temperature is in Kelvin. This is, but people forget this often. And guess what? They will get the wrong answer. If I raise the temperature to 350 Kelvin and lower the pressure to 1.5, and my units match up, atmospheres to atmospheres, what is the new volume? So this one is just the same as this one in terms of rearranging it. So essentially I'm going to get 350 times 2.3 times 17 and 1.5 times 299 on this side. This side will be V2. Okay, so if I do that math, I will get around 30.51 liters. Okay, we only have 2 more problems and we should be done for the day. Let's go ahead and check these out. A gas that has a volume of 28 liters. Pressure times volume over temperature. 28 liters. A temperature of 45 degrees Celsius. See, now they're trying to be those old tricky people again. We have Celsius, got to convert. So 273 plus 45, we have 8. 318 Kelvin. And an unknown pressure. So this is a little bit different. I don't know what this pressure is here. And its temperature is decreased to 35. So 273 plus 35 is going to be 308 Kelvin. Its volume is increased to 34. So I'll put 34 right here. And the pressure is now 2. If if I measure the pressure after the change to be 2. So yet again, sometimes you've got to figure out what they're asking here. What was the original pressure of the gas? So to isolate this, I'm going to have to multiply both sides by 318 over 28. See, on this side, it will cancel. On this side, I'll get 318 over 28. So that's going to be my pressure. So I should take 34 times 2 times 318 divided by 308 times 28, and I should get 2.5 atmospheres. Okay? All right, moving on down. The last one. Pressure times volume over temperature equals pressure times volume over temperature. A gas has a temperature of 14 degrees Celsius, so convert to Kelvin, 287, and a volume of 4.5. If the temperature is raised to 29, so I'll have convert that to Kelvin, and the pressure is not changed, what is the new volume? So this one's a little bit different. You're like, well, wait a minute. They didn't give us the pressure. So we don't have all of the numbers here to put into this equation. Now, if they do that, just put 1. Because it said, the pressure is the same, so what does it matter? We'll just say the first pressure is 1 atmosphere and the second's 1. So it doesn't really matter as long as it's the same number, but it's easier for us to put in 1. And when you think about it, this is actually volume over temperature equals volume over temperature. So this is actually kind of like Charles' law here. But you can use the combined gas law to complete all of those answers. Just put 1 in for the other unknown. So yet again, we can just rearrange the equation. V2, so we'll have 302. So if I multiply both sides by 302, right? I will, and that 1 doesn't matter. This 1 doesn't matter. So essentially I have 302 times 4.5 over 287 equals my volume. If I do the math, it will be 4.7 liters. And yet again, I could take that number, plug it back into my equation, and see what the answer is. Okay, that's the end of the lesson. We've gone over 4 different gas laws now. We should know Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. In the next video, we're going to go over something called the ideal gas law, which kind of throws in moles, and it has some constants. I think it's kind of interesting. And then we should be done. Well, we also have to do Dalton's law, but after that we should be done. So if you have any questions, let me know.